Okay, so let's start with the case where our object is far from the lens. Okay, now far is a relative term. We could be looking at a star that's extremely far away. It'd be hard to draw that here. In fact, we could assume that's almost infinitely far away. But let's assume we're looking at an object. In this case, it's 4 times the focal length away, I believe. So the focal length is 2 units on here. That would be 4 units, and we're 8 units away. So let's consider what that would look like, and then we'll actually do the calculation using the lens equation, right? So ray number 1 in parallel, and it's going to pass through the far focal point. All right. Ray number 2 needs to pass through the near focal point in order to get that correct. It's good to sort of sketch it in lightly and then draw it more confidently. That has to come out parallel. So I'll try to stay sort of parallel to that line on the grid. So it looks like I will have an image over here that once again is a real image. It's an inverted image, and it is small. Okay, so it has a negative magnification whose absolute value is between 0 and 1. It's smaller. It looks like maybe even half the size. And I'm not sure if that's exactly right, but we'll see when we do the calculation. Now let's check that out. Let's put in the last ray. Just as our confirmation, I'm going to try to draw a ray that goes right through the middle of all of this. It's a straight line. It's actually easier to do than the mirror. You can, if you have a ruler, you just straight line it through the middle of everything. And you can see that, yes, it kind of confirms that the first 2 rays did meet at the right place. Okay, so I have my 3 primary rays drawn. Remember, there is light going in all directions, everywhere in between those directions as well, and even away from the lens. But we're looking at those 3 primary rays to get we need at least 2 of them to find out where the light rays will intersect. That's what we would see. Okay, now to see it, let me make it clear. If your head were here, where I just put the blue arrow, the light would not yet be in focus, so you would not be able to see it. Okay. In fact, because this is a real image, we actually could put a screen. If I put it where I put the blue arrow is, it would be a fuzzy image, right? If I put the screen way back here, the light has already spread out again, so that would be a fuzzy image. But if I were to put the screen right here, this image would come together on the screen and be very focused. So you can take a magnifying glass and a piece of paper and get something from, hold it near the window and use the magnifying glass and the paper to bring in an image of what's outside, and you'll see it's small and upside down. Now let's use the lens equation here, and let's assume that DO is equal to, let's just write that it's 4 times F. Okay, so if I put that into the thin lens equation, we get that 1 over 4F plus 1 over DI. We don't know what the image length is yet. We can see from our picture, I have a guess about that, but I won't write it in yet. It should equal 1 over the focal length. So remember 4F, we're just assuming DO is 4F, so we fill it in and it looks like that. So 1, move this up, 1 over DI, I can move it up, I think, better, is equal to 1 over F minus 1 over 4F. If we consider 1 over F to be 4/4, we then end up with 3 over 4F. So then DI is 4/3 of F. So it's sort of 1 1/3 focal lengths away. What should the magnification be? Well, the magnification should be negative DI over DO, so negative 4/3 of F over DO, which was 4F. And if we do a little bit of multiplying, we'll see that that's, let's see, I'm going to go times 1/4, that will be negative 1/3 as a magnification. So it's smaller about a third of the size, and it is upside down as we would have expected. Okay, so we're going to now move the object in closer to the focal point and see what happens. Okay, so now we have an object that's about half the focal length away from, it's about 1.5 focal lengths away from the lens. So let's see what that does. So it's still outside of the focal point, but it's close to the focal point, the near focal point of the lens. So ray 1 goes in parallel and out through the far focal point. Ray 2 needs to go through the near focal point. Now this may almost go off my lens for the sake of, you could just pretend your lens is an infinitely long vertical line. Because of the assumptions we've made, it will work and give us the correct answer. So that light ray would go parallel and look something like this. In reality, if you got that close to the edge of the lens, it's probably going to have some aberrations, but this is a theoretical schematic. So this gives me an image that looks something like this. You can see the image is further from the lens than the original object, and it looks like it's bigger. Okay, so the light rays really do meet. If I put my eye back here, I would be able to see that those light rays really meet. Or better yet, if I put a screen right here, I could actually get the image to show up clearly on that screen. Once the image would be formed on the screen, and then light would bounce off to viewers all around the room, and they would be able to see that image. All right, so you would reflect the image off of the screen for everyone else to be able to see. Okay, rather than if you don't have a screen, you need to be standing over here where those eyeballs are in order to see the image. And if we put the screen too far forward or too far back, we get blurry reflection instead of a nice crisp reflection. Okay, now let me put my third ray in just as verification. That's the one that goes right down the middle, and it should continue going straight, and we can see, yeah, it's pretty good. Okay, so all of this was done freehand. If I were using rulers, I could get those, and was very careful, I could get those to meet up nicely. Okay, so as I said, we're expecting a real inverted, but this time larger image. So all of those things are true about the image. It's real, inverted, and large. Okay, so let's put some numbers in to see what happens. In fact, let's just say DO is 3/2 of the focal length. So we're 1.5 focal lengths. That's what this picture corresponds to. So DO is 1.5 focal lengths out. So if we substitute that into the thin lens equation, 1/3/2 F plus 1/DI should equal 1/F. Okay, so 1/DI is equal to 1, I'm just going to write this as 3/3F minus, and then the term I'm bringing over could be 2/3F. So 3/2 F, when you take its reciprocal, would be 2/3F. Okay, so we subtract that, and we can see that we would have 1/3F left. Okay, so DI, just check and make sure I got that right for a second. Oh yes, everything looks good. Okay, so DI would simply be 3F. My picture is just off a little bit. I should have had 3F would be back there in the picture. So because I was freehanding it, I didn't get my rays quite right. I think ray number 2 sort of went upward a little bit, so it met a little bit earlier than it should have. So if I drew everything a little bit better, it would in fact be the answer. Maybe the moral of the story here is that the equations give you the answer. The sketch is really nice for knowing what kind of image you're looking at. Okay, so it helps you understand how the light would come together. But if you want to know really where the light comes together, you ought to use the equations. Let's use the magnification formula. So it's negative DI over DO. So negative 3F over 3/2 F. And if you look at that, you'll get negative 3 times 2/3, negative 2. So Sure enough, the image, if I did everything correctly, should look twice. The lateral magnification should be twice that of the original object. So you can see the image is larger. It's not quite in a 2-to-1 ratio, but it should be in exactly 2-to-1 ratio given those numbers. So we're not going to do the case at the focal point. The light actually will never converge. The light rays will come out parallel on the far side of the lens. So you could never form an image there. So that leaves one case where the object is inside of the focal points. So let's look at that case. Okay, so here I've redrawn everything. And let's see, we have a lens. I made the focal points further out. So it's a weaker lens. As f gets bigger, the strength of the lens gets weaker. I'll talk about that in just a moment briefly. I just did that so that we could get a picture that is easier to draw. Otherwise, angles get too large and it's hard to see what's going to happen. So I'm using a weaker lens here, but the object is now inside of the near focal point. So it's less than the focal length away from the lens. So light ray number 1, in parallel, out through the far focal point. Okay. Now here's the important thing. This one's a little harder to draw. We now need to use the near focal point. We can call that focal point number 1. We were supposed to go through that and then come out parallel. But we can't go through it. But we can have a light ray coming off of, remember light rays are coming off in all directions. One of those directions happens to be directly away from the focal point. So the light didn't actually go through the near focal point, but it's coming directly from that direction. So ray 2 now we know comes out parallel. Better job than that. Okay, so that's what ray 2 looks like. Okay, now consider what eyeballs would see. If we put some eyeballs out here, they would see that these light rays are not meeting over on the transmission side of the lens, okay, the right-hand side. They would perceive that these light rays had come from behind the lens. And I don't know that I have this quite right, okay, but if we extrapolate those lines backward, we would see that they had met back here. Okay, so what would this give us? This would give us an image that's a large image, but the rays are not actually coming from the place where we see the image or perceive the image. So since it's a perceived meeting of the rays, we have a virtual image, right? Looks like it is an upright image. Okay, and we can also say that it is a large image. So the magnification is greater than 1 in value. In fact, it's a positive magnification. Let's put in our third ray just to verify that this is in fact correct. So the third ray should be no different. That's the ray that goes right through the center of the lens. And we can see that's also spreading out. These rays are getting further and further apart. So the viewer would see that that ray had come from back here, about where I kind of curved that a little bit. I don't think I got the image in exactly the right place, but close enough. So if there was an eyeball over here or we were moving around, we would also see the tip of the image coming, you'd see that going through where we've just located the tip of the image. All right, so all 3 rays would in fact give us the image location being behind the lens. If we put any 2 of them together, we would see that they meet back on the left-hand side of the lens, giving us a virtual image. All right, now imagine we were talking about projecting images on a screen. If you were to put a screen here, those light rays do not come together in a focused manner. Okay, if you put a screen here, same thing is true. What would happen if you put a screen back here? Okay, the answer is nothing, because the image doesn't really come from that location. You're projecting the light forward to the right, not backwards. So if we put a screen back there, we would just see a screen behind the object. Okay, so when we look through the lens, the image would not form on the screen. The screen would just be another object that we could look at looking backwards. All right, so This gives us a large image, but the only way to see that image is with our eyeballs from over here. Okay, we cannot get that virtual image to show up on a screen, but we can look back through the lens to see where it's coming from. In fact, because the light doesn't actually come anywhere, we could move our eyeballs up really close and they would still see that image in the same place because they're watching light ray, they're looking at light rays that are diverging rather than converging. So we can put our eyes anywhere on the right-hand side and still see that. Now let's quickly look at the thin lens equation. Oops, let me get rid of that keyboard. Let's pretend in this case that DO is exactly half of the focal length. Okay, so using the thin lens equation, we would have 1 divided by f over 2 plus 1 over di equals 1 over f. If I put that together, I have 1 over di. Don't try to solve it in one step. It's 1 over f minus, now I can say this is 2 over f. If I take the term on the left-hand side and subtract it, I can rename that as 2 over f. This gives me negative 1 over f, okay? Now we can see, what does the negative mean? Oh, so this means, by the way, di, I should solve for di, is at negative f, all right? So now remember, f was the focal length. If the image showed up at positive f, we would see it showing up at the focal point on the transmission side, okay? The side where the light is transmitted. So what does the negative mean? It means it shows up a distance of f on the side the light came from. Okay, it's supposed to form on the transmitted side, but instead the image formed on the other side. So this is a virtual image that is on the same side of the lens as the light originally came from. Okay, and it's exactly f away, which is why it lines up with that focal point pretty nicely in my picture. So I drew it pretty well. Let's consider the magnification. That should be, switch to black here so it reads better, negative di, so that's negative f, over, let's see, over do. Oh, do was an f, do was f over 2. I was confused for a moment. I thought I was going to get a 1. Okay, so when I look at that, I should get a positive, and I will get a positive 2. Just a little bit of work with fractions. So my image is upright. That's what the positive means. It's large because it is twice as big as the original object. So now we can move things around. We could look at all kinds of cases in between the ones that we looked at. But in general, as soon as the object is inside of the focal point of the lens, we switch to virtual, upright, large images. Right? One final note on lens strength. Many of you wear glasses or have contacts, all right, and the prescription is actually in diopters, okay? A diopter is really a 1 over centimeter, okay? The strength is given by 1 over the focal length of the lens, all right? So let's say that you had a lens on your face where the focal length was positive 50 centimeters. Turns out the focal lengths of these lenses are pretty big because they're only helping your eye to focus the light. You wouldn't want a lens that's doing a lot of focusing. It just needs to adjust what your eye can do. So if you had a focal length of plus 50, that would correspond to a strength of, let's see, these are in centimeters. Oh, I'm sorry, this should be per meter, right? So a focal length of 50 centimeters is 0.50 meters. So if you put 1 over 0.50, that would be a prescription of +2 diopters. Okay, so some of you who are actually farsighted, means your eye doesn't focus the light quite enough. So you want a convex lens, like the ones we've been working with, that would help you to focus the light a little bit better. If on the other hand, you were nearsighted, you might have a focal length of say Let's go with negative, let's go with negative 0.25 centimeters. Okay, so you would have the other kind of lens, which would be concave, because your eye is actually over focusing the light. So you need to put something right in front of your eye that helps to spread the light out. And so what would the strength be? The strength would be 1 over, I'm sorry, that was 25 centimeters. So that would be negative 0.25 meters. So 1 over 0.25, which would be positive 4. That would be actually a very strong prescription. You'd be extremely nearsighted if you had that prescription. So I know that, I'm around a, I'm sorry, it should be a negative, because that was a negative 0.25. Oh, let me make that correction here. Let me put this in blue. It would have been a negative 0.25, so a negative 4 diopters. I'm fairly nearsighted, and I have a prescription of around negative 2.5. So negative 4 would be pretty extreme. You'd be close to legally blind without your glasses. So it would require actually pretty thick lenses if they were made out of glass. So that's how the prescriptions work for eyeglasses. You're simply taking 1 over the focal length measured in meters, and that's the diopter strength of your prescription. If you are farsighted, you need a lens that helps you to focus. So you have a convex lens added to your eye. And if you are nearsighted, your eye is actually over focusing, and therefore you need one that spreads out the light. Turns out if you're nearsighted, actually you're very good at seeing things that are very close. In fact, you can see things that are up close better sometimes, but that's not very useful if you want to, say, play baseball and the ball is fairly far away. It makes it kind of hard to see the ball and hard to hit it. So you would certainly want a prescription so that you can play baseball, or perhaps to drive your car.